Hello everyone, welcome back for some examples of doing the hypothesis testing with two populations, which is of course section 11.1. We're carrying on doing these notes. And this example right now we have this context. It says in the October of 1947, the Gallup organization surveyed 1,100 adult Americans and asked, do you totally abstain from drinking alcoholic beverages? This is 407 said yes. They did the study again in 2010, and 333 said yes. We're wanting to test this hypothesis whether the proportion who abstain has changed, and that's going to be a key for us, whether it has changed or not. That's going to help us determine how we should phrase the alternative hypothesis, and then we're using alpha of 0.05. So of course, with the hypotheses here, we're comparing population 1 with population 2, where population 1 is going to be the population originally surveyed, so that's the people in 1947. And then population 2 is going to be the new survey, if you want to call it new, which was in 2010. And we just have to determine, well, of course, there's nothing to determine about the null hypothesis. We always will say equals for that one. So the null hypothesis will be that population 1, or the proportion for population 1, I should say, is equal to the proportion for population 2. And then the alternative hypothesis, it says we're just testing whether it has changed. So we want to say is not equal. We're not talking about whether it's increased or decreased, only if it has changed. And then alpha we saw is 0.05. We get that one there. And now we're ready to just go straight into the calculator with this one. We want to go to stat, over to tests. And of course, we're looking for two proportion because there's two populations over here. Two proportion z test because z goes with proportions. Now, x1, that should be the number of successes for population 1, which in this case, a success should be somebody saying yes for the question. So that was 407 people out of 1,100 that were tested. The people who said yes for population 2 was 333, which is also out of 1,100. And we are checking for not equals because we just want to see if it has changed or not. We will calculate this one. And we get a test statistic of I will round it 3.34. The p-value, you notice it goes times 10 to the negative 4, so this is a very small one. It goes, I will even just write it, what we should move 4 spaces to the left, so there will be 3 zeros in front, 1, 2, 3, and then we'll go 8. Well, let's just do that one. In this case, we are just checking whether the p-value, which of course has to do with the probability to get such a test statistic as this, which of course by now we've learned that getting a z-value of 3 is a pretty high one. In that case, the p-value, when we compare it to the level of significance, which is just 0.05, it's much less. So as we did in chapter 10, we will reject the null hypothesis. It is too improbable, it is too unlikely to get such a test statistic as this if the proportion has not actually changed. So we would like to say that there is, in our conclusion now, we will phrase it kind of the same way that we did before. There is sufficient evidence to conclude, and then at this point we want to basically restate the claim that we're checking to conclude that, I will say that, and then we want to put in here, and of course you don't need the parentheses or if I can select the right terminology for this punctuation, is called quotation mark, goes here, this part, proportion of adult Americans who totally abstain from alcohol has changed. We want this thing to go here. There is sufficient evidence to conclude that the proportion of adult Americans who totally abstain from alcohol has changed. We'll go there. Very good. And we're going to knock out another example real quickly for this one, and then we will see something else, which is going to be how to use confidence intervals rather than just doing the hypothesis testing, or else We will test hypotheses by making confidence intervals for something else. We're going to see that after this example, but let's get into this one. It says, in a study of red-green color blindness, there were 500 women and 2,100, or 500 men and 2,100 women were selected randomly. Among the men, 45 had color blindness, and among the women, 6 had color blindness. So you can tell, obviously, color blindness in men appears to be so much more likely that they did not have to select as large of a sample for men as they did for women. They probably chose such a large sample for women just to hope that they will get at least one colorblind woman, because it appears to be quite rare. But what we're going to test is whether there is sufficient evidence at this level of significance, 0.05, to support the claim that men have a higher rate of red-green colorblindness than women. So we can say that the population 1 must be probably, well, it doesn't really matter too much, will be the men, and population 2 can be the women. We could do it the other way around, and it wouldn't change anything. It would only change probably the symbol that we will use with the alternative hypothesis. We would just reverse the direction of the inequality, because I suspect we're about to use an inequality. Let's see, we will have, of course, population 1 and population 2 there, and for null hypothesis, no matter what, it always just says equals. And then alternative hypothesis, we already arbitrarily set that the population 1 should be the men, and so we're checking whether there's sufficient evidence to claim that men have a higher rate. So we want population 1, we're testing whether that is greater than population 2, or I should say proportion 2, which is going to be the proportion of women that are colorblind. Alpha level, it just gives it to us explicitly there. And now we're ready to do the calculator buttons. It's so convenient. We will go to tests, to prob z test, and let's get the new numbers in here. Population 1, we had 45 colorblind men out of the 500 that were sampled, and then we had 6 colorblind women out of the 2,100 that were sampled, and we want to see whether the proportion for men was greater, so we want the greater one, than the proportion for women. Let's calculate it. Wow, look at that p-value. The test statistic here goes 12. I don't think we've seen such a z-score so far in this class of 12. The p-value, I cannot write it because it needs 37 zeros, or it would be 36 zeros and then the 7 after the decimal place. It goes like so many zeros. There's 36 of them, and then 7 6. So there can be very little doubt. Of course, by doing these kinds of experiments, we don't necessarily prove anything, but I think that by some means it must be possible to prove that it's more likely for men to be colorblind than women. We would, for sure, based on this p-value, it is much less than the level of significance. And we can say very confidently that there is sufficient evidence to conclude that, and what are we wanting to conclude? It's up to you to finish this one. There is sufficient evidence to conclude that, I'm going to say what mine would sound like, that there is, that men have a higher rate of red-green colorblindness than women, period. It would be a well-stated conclusion. So that does it for, I believe, for these examples like that. We will pick up in the next video talking about using confidence intervals in this section to test a hypothesis. Catch you soon.